Hello everyone, I am Milash Hain and the title of the research paper I selected for my independent study is Fast and Efficient Algorithms for Computational Electromagnetics on GPU Architecture, which is published on the journal IEEE Transaction on Nuclear Science, which is written by Tortvidas Machena, Paolo Bettini, Gabriel Menducci, and Mauro Passarotto. Magnetic confinement fusion is a mechanism of generating thermonuclear fusion power and confining it in the form of a plasma using magnetic fields. As you can see here in the middle, the plasma is formed by combining deuterium and tritium atoms to form helium atoms. The loss of mass is converted to energy according to Einstein's equation, which is energy equals to mass times the square of speed of light in vacuum. This plasma can cause damage in the walls of the magnetic confinement fusion devices. Therefore, it should be prevented from approaching the edges of the machine with the use of a circulating magnetic field. Therefore, efficient methods should be used to perform diagnostics in MCF devices. The objective of the study is to test how efficiently magnetic measurements can be obtained using GPU architecture, because it's very important to obtain real-time measurements to identify unstable conditions and hazardous situations in magnetic confinement fusion devices, and then take necessary precautions. The GPU implementation is totally based on parallel computing. Since there are hundreds of thousands of sensors that are being used, iterative calculations cannot be done since the data from each sensor should be obtained all at once. When using CPU implementations, it is more likely that each sensor is considered one at a time. For example, if we consider to analyze 1000 sensors, at the first iteration only the first sensor will be considered and the rest of the 999 sensors will be on the queue. Once the calculations are done for the first sensor, then only the calculations will start for the second sensor, and the process will go on till the sensor number 1000. To reduce this fall time, GPU implementation creates different threads for each sensor as seen in the first line of the pseudocode. Within each thread, the magnetic potentials and magnetic flux densities will be calculated using predefined mathematical formulae as mentioned in the second line of the algorithm. At the end of each calculation, the results will be copied to the CPU RAM according to lines 5 and 6 of the code. The researchers have applied the GPU architecture for few test problems to validate and show the efficiency of the method. In the first case, magnetic flux density of a brick-shaped element with a uniform current density was obtained. The results were obtained along a line parallel to x-axis where y equals to 0.25 meters and z equals to 0 meters, whereas the element was centered at the origin. The results obtained using the GPU architecture was compared with their respective analytical values. The dimensions of the brick-shaped element is given on the screen, which has a width of 1 meter and a length of 1 meter and a height of 100 meters. In the second case, magnetic flux density is produced by an eddy current on a current density induced by a sinusoidal magnetic field was considered. The sensors were placed on the node of 15 by 15 grid, and the GPU computed results were compared with the results obtained using Biot-Savart's law. And the uniform sinusoidal magnetic field, which was used as an amplitude of 1 Tesla and a frequency of 50 Hz. For the final case, the radial component of magnetic flux density of a RFX mod machine was obtained using a 181 by 180 grid of sensors placed on its toroidal surface. A two-dimensional graph was obtained to show the variation of radial magnetic flux density with the change of toroidal and poloidal angles of the device. So as you can see, the RFX mod machine is known as the oldest device which is built to confine plasmas using magnetic fields. Considering the results for the case of the brick-shaped element, the analytical solutions and GPU related solutions were plotted on the same graph. On the x-axis denotes the x-coordinate and on the y-axis it shows the magnetic flux density. The red colored stars denote the analytical solution while the blue colored solid lines shows the values obtained using GPU routines. In this case, the researchers were able to find a perfect agreement between the methods analytically and GPU. And considering the case of the conducting plate, the researchers had shown that the results obtained using GPU architecture and the results obtained using Biot-Savart's law had agreed well. And also the most significant part is the researchers were able to notice an increase of speed in the computation which is 2 times greater than the values obtained using CPU. As you can see, the red colored curves shows the direction of the eddy currents, and these blue colored dots denotes the sensors which is used to obtain magnetic measurements, and these blue colored arrows shows the direction of the magnetic flux density which has occurred due to the eddy currents. Now let's consider the case of the RFX mod machine. The picture on the left shows a piece of a shell of RFX mod device. The red colored cones shows the direction of eddy currents. After plotting the 2D graph, it was observed that the radial component of magnetic flux density was not uniform at a toroidal angle of 90 degrees. The reason for that was identified as the butt joint effect which was caused by the poloidal gaps. So in this case, it clearly shows that an error correction should be done at poloidal gaps using necessary methods. When it comes to the discussion, the first case of the experimental series shows that the results obtained using GPU architecture is accurate as the analytical solution. Provided with correct mathematical expressions, magnetic flux densities can be effectively calculated without analytically solving. The second case shows that the method of using GPU computations are much faster, which in turn helps to obtain real-time magnetic measurements. On the third case, considering the RFX mod device, it pointed out that the errors in MCFs can be detected using GPU architecture. This will help scientists to avoid inconsistencies in MCF devices in the future. Finally, we can say that GPU implementation cut down a lot of time by obtaining instantaneous magnetic measurements. And also GPU architecture reduces time consumed for analytical calculations on magnetic flux densities. For example, the magnetic confinement fusion devices usually occupies a lot of area. So to obtain magnetic flux densities and magnetic vector potentials, we have to consider about hundreds or thousands of coordinates on the surface. So to obtain using analytical solutions, it will be a very tedious task, and there is a chance that at least one calculation will be an error calculation due to human errors. So to solve this, the GPU architecture can be easily used provided that the mathematical expressions for vector potential and magnetic flux densities are correct. And then the GPU architecture can automatically calculate the values in real time. And these experiments can be redone using different sensor configurations. For example, if we consider the case of the conducting plate, even though the researchers have used a 2D grid, a 3D grid can be also used to obtain the difference in magnetic flux density with the distance between the conducting plate and the field of the point. And this concludes the presentation. Thank you for your patience and attention.